Hello everyone, in this video I will introduce our work 3D point cloud generation with MilliWave radar. A wide range of sensing modalities are already available on vehicles, such as cameras, Lidar, and radar. Visual sensors like cameras and Lidar are vulnerable to adverse weather conditions, such as rain, snow, and fog. In contrast, radar can penetrate small water particles and can make autonomous driving more robust against bad weather. However, vehicle radar has two main drawbacks. First, the radar has low spatial resolution due to its small form factor. While visual sensors reveal fine-grained shapes of targets, radar only generates intensity maps with strong reflection peaks. Second, vehicle radar typically emits millimeter-wave signals, which are specularly reflected by most objects and may not be captured by the radar. These figures show the aligned camera images and radar intensity maps of different vehicles. The radar can only see parts of the vehicles with strong reflections towards the radar. Recent innovations in millimeter-wave sensing non-coherently fuses the measurements along the radar's moving trajectory. While to some extent alleviating the specular reflecting problem by illuminating the target from diverse locations, their imaging resolution is still limited by the physical size of the antenna array and cannot be fundamentally improved through spatial sampling. To solve this problem, we propose MilliPoint, which enables synthetic aperture radar imaging with low-end vehicle radars. MilliPoint coherently combines measurements of the radar to generate dense and high-resolution 3D point clouds. The first challenge is that SAR requires accurate tracking of the radar. The figures below show two cases where the radar moves along the cross-range direction at a constant speed and an accelerating speed. Without knowledge of the radar's location, the image of the object can be highly distorted. To solve this challenge, we propose a self-cross-range tracking method. We let the radar estimate its instantaneous speed. We exploit an observation that different transmit-receive antenna pairs of the moving radar experience similar channel responses with a time delay. An intuitive example is shown in the left figure. The radar has equally spaced 4 antennas. As the radar moves, the first antenna pair at time t1 coincides with the second antenna pair at time t0, so their measurements become highly correlated with a time delay of t1 minus t0. Meanwhile, the radar moves by one antenna spacing, so the speed of the radar can be calculated. In general, for any two antenna pairs, the cross-range moment is the average of the spacing between the transmit antennas and that between the receive antennas. The elapsed time is the delay time of the measurements of the two antenna pairs with the highest correlation values. The second challenge is that SAR requires focusing on the center of the target. The figures below show the scenario where a metal surface is 3 meters away and has an incident angle of 135 degrees with a cross-range direction. If the SAR focuses on the broadside direction, then the target disappears, as in the left figure. Only when the SAR focuses on the direction of 45 degrees, the target is imaged, as in the right figure. The root cause of this phenomenon is the mismatch of the physical aperture of the radar and the effective apertures of the targets. The physical aperture represents the physical trajectory of the radar. The effective aperture of the target is a segment of the trajectory where the target's reflection is received. As shown in the figure below, due to specular reflection, the effective aperture of the metal surface is a short red segment, while that of the wall is the blue segment and the same as the physical aperture of the radar. In the paper, we prove that the focusing center can be represented by the parameters L and theta, which can be identified in the spatial frequency spectrum. On this basis, we propose a multi-focusing algorithm to overcome the specular reflection problem and image all objects in the environment. The final challenge is that SAR only generates 2D intensity maps. The figures below show an indoor scenario, where images of objects at different heights overlap with each other. To solve this challenge, we exploit multiple antenna pairs along the vertical direction. For each antenna pair, we generate one SAR image and find pixels with high intensity. In the paper, we prove that the complex pixel values do encode the elevation information. So we combine co-registered pixels of all SAR images to form a virtual pixel array and estimate the elevation of the pixels. The right figures show an indoor scenario captured by a stereo camera and a radar point cloud generated by MilliPoint. We conduct experiments using a TI cascade radar with 6 transmit antennas and 8 receive antennas. A Z stereo camera is used to capture the ground truth. We compare MilliPoint with non-coherent imaging and imaging with a static radar. In different scenarios with different objects such as cars, pedestrians, bikes, and trash bins, MilliPoint generates the densest point clouds and the points are accurately aligned with the objects and reflect their shapes. In conclusion, in this paper, we propose MilliPoint, which is the first step to enable high-resolution, high-density 3D point cloud generation on low-end vehicle radar based on SAR. We envision MilliPoint as a new type of sensor fusion modality. Thank you, and I'd like to take any questions.